So this is a quick intro to quadrature encoding. Quadrature encoders are a way of detecting which way along a line or around a dial something has moved. And the neat thing about quadrature encoding is we can also detect which direction that thing has moved or traveled. The two signals here allow us to determine the direction. So let's say that we've got a lathe saddles and we're sort of somewhere here, and the read head is displaying both A and B as being quite true or high signal here. So when we start to move, these signals are going to go up and down, and they go up and down every 2 or 5 microns, something like that. It depends on the scales. 5 microns I think is like 2/10,000ths of an inch, but that's just using mental arithmetic right now. Don't quote me on that. 2 or 5 microns are pretty common for glass scales. So let's say that this direction is towards the tailstock and this direction is towards the headstock. As we move from here, where both regions are true, we move over to this section where only the B region is true. We know that we've moved towards the tailstock because B is high and A is low. But let's say we moved the other direction. So we're starting here and we're going to here. We now see that A is high and B is low. So we know that we've moved towards the headstock. This is also how rotary encoders work. Rotary encoders are common on electronics where, like, say you've got a volume control and you can keep turning it and it never actually reaches a hard stop. The dial just keeps on going around and around. And you can also use that for things like detecting modes and stuff. They basically use this same signaling, but with only 12 counts per revolution rather than 5 microns or 2 microns per count or per tick. So that's kind of what's going on in these sorts of things. James Clow of Clow 42, he used a rotary encoder on his lathe spindle with 4,096 counts in a revolution. So that's sort of a little bit over 10 ticks per 1 degree, 1 degree, or 10 counts per 1 degree. And that's how he counts the spindle position in his electronic lead screw project. There is also one other thing, which is sometimes there's a reset line, and that reset line comes up and it comes back down again. And what this does is, because sometimes you move the carriage so quickly, the computer might miss one of these steps, and so it becomes out of sync. What the reset line allows you to do is every 25 millimeters or about every inch, if the reset line, which is sometimes called Z, when that goes high, that allows the computer to go, I've missed a step, and it just allows it to resynchronize. And that's all that one is. On rotary encoders, typically the Z is once per revolution, so that if the counter is lost, it can basically resynchronize. And you could also use it as a tachometer just by monitoring the Z line, but that's probably for another story.